Hi mathematicians, let's go ahead and talk about a different method for solving for a limit, and it's called the squeeze theorem. And so basically what it's saying that if you have three functions, or rather you have a function of interest g of x, and near your point of interest, it lies between these two other functions, that you can use that to determine the limit of this guy. And so I'll elaborate in a minute. So he's like, help, I'm stuck in between. Let's see if I can make this little bubble. Help, I'm stuck. Okay, so the idea is this g of x, what you're interested in, is stuck in between these two others. And so we say if the limit of f of x as x approaches a equals the limit of h of x as x approaches a, and they both equal L, some value L, this is an h, then we know that the limit of g of x as x approaches a also equals L, right? So the limit of both of these is L around this value a, and g of x, it always lives between them. Then it makes sense that we can say that that limit of g of x as x approaches a is also L. All right, and so let's look at that graphically real quick. And so here, this is from your book. We have the function sine of x, and obviously it goes through 0, right? When x equals 0 to equals 0, it comes up here, peaks around 1, or at 1 rather, at pi over 2. Its minimum value is -1 at negative pi over 2. And they're making the statement that this g of x, this sine of x, always lives between this blue function, which is f of x equals negative absolute value of x, and this red function, which is h of x equals absolute value of x. So we have those two functions. And so if we were asked what the limit of sine of x was, is x approach. So let's go ahead actually and do that. So let's look and suppose we were asked the limit as x approaches 0 of sine of x. Actually, let me erase this up a bit. Okay, and so we're making the statement that sine of x is always less than or equal to x, greater than or equal to negative absolute value of x. And so then let's look at the limit as x approaches 0, a negative absolute value of x, that equals 0. The limit as x approaches 0 of absolute value of x also equals 0. And since we know that sine x is always between them, it makes sense then that this is also 0. Okay, so, and again, this is the graph, the visual representation of what's going on here. Okay, so let's go ahead and do another kind of algebraic solution to one of these squeeze theorems, or use the squeeze theorem again. So use the squeeze theorem in this example. Use the squeeze theorem to verify that the limit of x approaches 0 of x squared sine 1 over x equals 0. Okay, so we have to figure out what is this always between? What is this function between? And so let's take a minute and just look at this portion here. And what do I know about this portion? I know that sine 1 over x is always between -1 and 1, right? It doesn't matter what you have here, right? If we're talking about the sine of something, it always has to be between 1 and -1, right? Somewhere between them. It oscillates back and forth. So I know that. All right. What else do I know? I also know that x squared sine 1 over x is always less than or equal to x squared, but greater than or equal to -x squared. Okay, and so how do I know that? Well, it's easy to make this statement, right? If I were to cover this up, it makes sense that -x squared is always going to be less than x squared. And x squared is certainly going to be equal to x squared. So we can make that statement all alone, right? And then what's going to happen up here is, depending on this value of sine 1 over x, you're going to be somewhere on either side, right? So we can go ahead and make this statement that we know that -x squared, right, is always going to be less than. Another way to look at this, actually, what you might want to look at, is we can just multiply this whole statement up here by x squared, right? And that might be a better way for some of us to look at it. So imagine I multiply this whole thing by x squared, right? Here I get -x squared. Here I get x squared, right? And so imagine if this is true, then just multiplying everything by the same thing, that this is also true. Okay, so hopefully I've convinced you that this lives in between these two other functions. So let's go ahead then and look at the limit as x approaches 0 of -x squared, and the limit as x approaches 0 of x squared. And wouldn't you know, they both equal 0. Therefore, the limit of x approaches 0 of x squared sine 1 over x, right? The limit of this as x approaches 0 is 0. The limit of this as x approaches 0 is 0. This guy's in between those two. Clearly, it must have the same limit. Okay? And so that is the squeeze theorem, just another way to solve for the limit in section 2.3.